m naught is equal to 0, in that situation, we end up getting E is equal to Pc. So this is an expression that is valid for a photon also, because ultimately photon is a massless particle. Its rest mass is 0, but it has momentum, it has energy, and their relationship is this. So P is equal to E upon C, that's it. Now what about the target electron? We assume that the target electron is initially at rest. So if it is initially at rest, it only has rest mass energy. E naught is equal to m naught C square, and its momentum is equal to, let's suppose, 0, right? P, I'm just writing P naught here is equal to 0 because it was initially at rest. Now this whole interaction takes place and the photon gets scattered in a particular direction at an angle theta with respect to the incident direction. In that situation, the photon loses energy. So its frequency changes, right? So now the photon, the scattered photon, has an energy h nu dash. You see, initially it had a frequency of nu, but now it loses energy because it provides some of its energy to the target electron. So it loses energy, its frequency decreases, and its momentum also becomes P dash, let's suppose we call it. So this is E dash and this is P dash is equal to, so P dash is equal to h nu upon C. But now the scattered electron has both rest mass energy as well as some kind of a kinetic energy. So let us write the most general expression, which is the expression for relativistic total energy. So let me write this. So the energy of the scattered electron, let's suppose E is equal to m naught square C to the power 4 plus Pe square C square root over, where Pe is the momentum of that scattered electron. So this is the picture. Incident photon with some energy gets scattered from a target electron. It exchanges momentum energy. The scattered photon goes in a certain direction with less frequency, and the scattered electron goes in a certain direction with a gained energy. So the loss in the energy of the photon is equal to the gain in the energy of the electron. So we can apply the conservation laws of momentum and energy in this particular picture. So first, let us apply the conservation law of momentum. So conservation of linear momentum. So the conservation of linear momentum simply says that the momentum of the photon initially plus, what is the momentum of the target electron? 0. So I can just write this in the left hand side, is equal to the momentum of the scattered photon P dash plus the momentum of the electron. Let me make it a vectorial expression. You see, momentum is conserved independently in two perpendicular directions. So along the x-axis, momentum is conserved. Along the y-axis, momentum is conserved. To make the calculations simpler, I have written the expression in vector notation. That means the overall momentum, so the vector quantity contains the x-axis component and the y-axis component, is conserved. So essentially, the momentum is conserved along the x-axis and the y-axis separately. I'm going to write that Pe is equal to P minus P dash. These are vector expressions, okay? Now, what is this? This is the difference between two vector quantities, P. Dash cos theta. Let me say that this is equation number 1. So based on conservation of linear momentum, I come up with this particular expression. Now I want to apply conservation of total energy, and let's see if we can use this expression there to simplify everything. All right. Essentially what you'll get here, lambda, lambda dash, lambda, lambda dash, lambda dash minus lambda, right? So lambda, lambda dash will get cancelled out and we will be left with lambda dash minus lambda. So I can just write it straight away as lambda dash minus lambda, which is equal to what? Lambda dash minus lambda is the wavelength shift or the Compton shift, right? Which is just del lambda, okay? So del lambda is equal to how much? H upon m naught c 1 minus cos theta. So essentially we finally have this expression now for the wavelength shift, that the wavelength shift is equal to h upon m naught c 1 minus cos theta, where h is a Planck constant, m naught is the rest mass of the electron, c is the speed of light, and theta is the scattering angle. So we have derived an expression for the wavelength shift or the Compton shift based on the particle picture of radiation by assuming that the incident radiation is composed of photons which are behaving like particles, and these photons are interacting with the electrons in the manner that two particles collide with each other. And by applying conservation of momentum and energy, we come up with this expression for the wavelength of the scattered photon.